Alright, today's episode is going to be all about caffeine. I'll see you inside. Alright, so looking at my notes, I think this is going to be the first in a multiple part series because caffeine is very complex. With that being said, by the end of it, you should know exactly how to use caffeine, how to gauge your caffeine sensitivity, and how to know if you're losing caffeine sensitivity. But today, we're going to talk a little bit of the nerdy stuff about the physiology of caffeine. So, caffeine is one of, if not the most highly exploited aid to enhance performance in a multitude of sporting events. And I think the most studied event is probably an endurance event, but caffeine seems to benefit just about everything. It also benefits things outside of sports like cognition, mood, and energy levels throughout the entire day. And caffeine has numerous effects on the body, such as increasing alertness, decreasing feelings of fatigue during a workout or just the day. And there are actually a few health benefits of coffee itself outside of the caffeine. With that being said, chronic reliance and dependence on caffeine in the end actually becomes deleterious to your energy rather than helpful. Alright, let's talk a little bit of biology. Caffeine itself is non-caloric and provides no energy in the form of carbohydrate, fat, or protein. Therefore, we do not actually derive any energy out of the physical molecule of caffeine. Instead, the benefits of caffeine come with its interactions with our nervous system and its ability to stimulate pathways involved in energy availability. So caffeine has different effects on different cells. Within the brain, caffeine is referred to as an adenosine antagonist. Adenosine is a molecule that will bind to an adenosine receptor within our brain, which sends a neuronal signal to our brain that we are fatigued. Adenosine is very interesting. It's kind of like an indicator of how long we've been awake. Adenosine accumulates throughout the day and is at its highest point right before we go to sleep. And when we sleep, the adenosine gets cleared out from its receptors and recycled to make ATP, and for numerous other functions. So when we wake up in the morning, we typically will have the lowest amounts of adenosine, and right before we go to bed, we'll have the highest. And now adenosine has receptors in the brain, which it will bind to, and when it does bind, it's a little signal of tiredness. And the more binding, the more tired. And what caffeine does is it pushes adenosine out of the way and it sits in this receptor, but it doesn't actually turn on the receptor. So adenosine can't get in and we don't get the signal of tiredness. I want you to think of wakefulness as kind of a push and a pull. There are certain chemicals in our body pulling our wakefulness down, such as adenosine. And there are other chemicals like adrenaline and cortisol that are going to be pulling our wakefulness up. And now when we feel like we have an abundance of energy, that means that this balance is shifted more to the pull side. And before we go to bed, or simply when we don't have energy, the balance is being pushed to a greater magnitude than it's being pulled. All of these molecules are always floating around our body. It's just the ratio of these molecules that will determine if we are tired or if we are wakeful. And now caffeine doesn't actually have the effect of increasing our energy levels. It has the effect of decreasing the signals of tiredness that would be pulling our energy levels down. That's why sometimes it's a little bit counterintuitive to take caffeine directly in the morning because those pulling forces are going to be at their lowest anyway. It might be a little smarter to take caffeine a little bit later in the day, but not too late that it affects your sleep, so that we can kind of clear out the mechanisms that would be pulling our energy levels down. However, we do have to remember that adenosine will still be building up when caffeine's inside the receptor. Caffeine doesn't actually block the creation of adenosine, it just stops it from getting in the receptor. So when the caffeine exits the receptor, the adenosine is just there waiting in the wings. So a lot of times, you'll get a buildup of adenosine while caffeine is in the receptor, and then when the caffeine begins to metabolize, a lot of adenosine floods the receptor. This is why many people feel an afternoon crash after they've had a large bolus of caffeine in the morning. See, this is one of the issues with caffeine. A lot of times we bolus it at one part of the day, and then there's none left at the end of the day, and a lot of adenosine is flooding the receptor. So we may feel a dip in energy, and there's two solutions to this. Either just live with the energy dip or take more caffeine. The problem with taking more caffeine is if we do it too late in the day, we don't get the adenosine when we do want it around to promote sleep. This is why trying to get the right amount of caffeine without having too much caffeine is very difficult sometimes. But personally, I would definitely lean on the side of not getting enough caffeine rather than having too much. With that being said, I actually think I have to turn back on my previous statement that caffeine doesn't directly increase energy. The molecule of caffeine does not increase energy. However, caffeine can increase the level of endorphins in our body. Endorphins serve a plethora of effects in the body, predominantly being an increased tolerance to pain and increased arousal. We actually naturally secrete endorphins as a response to pain and during exercise. This is why sometimes when you start exercise, it kind of feels painful, but once you start secreting endorphins, all the pain actually wears off. Endorphins simply decrease our perceived level of exertion, which simply means that at the same level of perceived work, we are actually capable of doing more. Alright, just to recap, the first and likely the main mechanism of caffeine is to decrease the blunting effect of adenosine. And the second effect of caffeine is to increase the arousing and pain mitigating effect of endorphin. Alright, now unfortunately for you, there is a little bit of biochemistry going on in this next one. The first two examples were things that caffeine does in the brain, and the next example is what caffeine can do to our muscles. Alright, so the endorphins released as a result of the sympathetic nervous system activity induce a series of events that stimulate calcium release from the endoplasmic reticulum. This is a membrane that surrounds the actin and myosin filaments and acts as a storage unit for calcium release and calcium reuptake. These actin and myosin filaments are the things that allow our muscles to contract. And the calcium is basically the energy that they use. The more of these actin and myosin filaments that are contracting at once, the stronger the contraction of the muscle. And the more calcium that is available, the more of these filaments will contract. To put it into perspective, when you grow larger muscles, you also grow more actin and myosin filaments. This is typically why larger muscles are also stronger and more forceful. Now, these endorphins have no effect on the amount of actin and myosin filaments that we have, but it does affect how many we can contract at once and how many we can continue contracting over a prolonged series of time. Now, the thing about actin and myosin is just because we have them doesn't mean they're going to be available to contract. They have to be in a specific formation that allows them to contract. And this is where calcium comes in. When calcium binds to a specific enzyme referred to as troponin C, the structure of the cell alters in a way that allow actin and myosin to move past one another and allow the muscle to contract. The calcium is then released from the enzyme and reabsorbed into this endoplasmic reticulum. Now, to the best of my knowledge, endorphins are responsible in almost all muscle contractions. It's just the amount of endorphins that we have that increases the strength of the muscle contraction. So it's a bit of a process. The more endorphins we have, the more calcium we release. And the more calcium we release, the stronger the muscle contraction. This all comes back around to caffeine. Caffeine will increase the amount of endorphins that are floating around our body and exuding this effect. And now another mechanism that caffeine works through is it actually increases the amount of fuel that's available in our bloodstream. What I mean by this is it causes our cells to release fatty acids and glucose molecules into the bloodstream, which can then be uptaken and used as energy inside other cells. This appears to actually just be a secondary effect of these endorphins. Endorphins don't just bind to the muscle, they also bind to other cells like fat cells, heart cells, and liver cells. This is where we increase the amount of glycogen and stored fatty acids that we have. Alright, so let's kind of summarize this one up. First, caffeine is going to decrease the tired promoting effects of adenosine. It's also going to increase endorphins. And these endorphins increase our ability to contract muscle, they decrease our perceived output, and they also increase our fuel availability. Alright, I think I'm going to end this one here. Today we talked about the physiological effects of caffeine and how it benefits our performance. I think the next few episodes will get into understanding caffeine sensitivity and when caffeine is not useful. I hope to see you next episode. Thank you.